In today's lesson, we will be using SFSpeechRecognizer, a new API to allow voice input for our local AI chat app. This topic is a bit more complex to implement as we won't really be living in SwiftUI land for this lesson. So I've already prepared all the code and I will walk you through it during the lesson. Parts of the code are also linked in the video description for your own reference, as I won't go through every single detail today. So basically there are three things we need to do. First of all, we of course need to implement a transcription service, and I've called it speech to text service in this project. Then we need to add this little dictation button down here. So this is just an SF symbol button. And then lastly, we need to pull everything together and use the speech analyzer in our existing business logic. So let's get right started. In our UI, we already have our save area inset for the bottom here with our text field and our send button. So these two things down here. And then we also added a second button with a microphone. So while we are recording, and this just basically flips a Boolean is recording, it shows one SF symbol, and then let me quickly turn that on. So this is the SF symbol while we are recording, and then this is the SF symbol when we stop recording. Of course, microphone stuff doesn't work in the simulator, so you'll have to run that on your real device. And before I forget about it, we'll of course need to have this privacy microphone usage description string in our info.plist file in order to get the hardware access needed for this feature. So now that we have our little microphone button in there, we either call start recording or stop recording, depending on what the current state is. And I've moved all of the new variables and both of the functions to the bottom of the file just for our reference, but I would advise you to keep all of the state variable and also the speech to text service at the top of the file so you have a nice structure. So basically we have our is recording flag, then we have a potential error message to show. We also have a transcription task and we need to store this here, but we'll get into that in just a second. And we also have our speech to text service, which we'll also go through in a minute. So then we have our start recording function and our stop recording function. Let's start by looking at the start recording function. What does it actually do? Because we're actually streaming audio here. So we make sure that we're not recording already, so this button can't be pressed twice. This is already somehow checked by the UI or by the button itself, but just to make sure nothing bad happens here. And then of course we set is recording to true. We create our transcription task, and this is just a Swift concurrency task, but we're storing it here in the variable so it doesn't get cancelled when this function is over, because we are streaming audio, so this task lasts for quite a long time, potentially until we cancel it manually in our stop recording function. So in there we await authorization to use the microphone and speech to text. Then we create a stream, and we'll look into what this transcribe function does in a minute. We have a for try await, so we are streaming in the partial results from the microphone, and we are assigning self.input to this new value, and self.input is just the variable that our text field writes to and the variable of the message that we send to our large language model. So basically we take the partial result and we assign it to our input. That way it also automatically gets displayed in the text field. And if there's any error, we will also assign that to our error message, and you can show that on your screen whichever way you'd like. Since we're already here, let's also briefly look into the stop recording function before we go into how the transcription using SFSpeechRecognizer actually works. So we make sure that we are actually recording, then we set it to false. We cancel and nil out our transcription task, so making sure that no new audio gets streamed into our text field variable. And then we also call stop transcribing on our speech to text service to clean up everything over there. So let's have a look at our speech to text service, and this file is linked via a GitHub gist in the video description, so you can check it out and download it over there or reference it for your own implementation. At the top here we have two wrappers for some old completion handler based APIs for SFSpeechRecognizer and AV audio session. I won't go into detail, you can look these up in the GST, so just concurrency wrappers to make our API a bit nicer to use. As I said, I won't go through this line by line because it is quite complex, but I will try to tell you the logic behind how it works. And then if you want to go into it yourself, you're free to check out the file or the documentation that I linked here on top of the file. So as you can see, there is quite a bit of code in here. So we have an authorize function. We have a transcribe function. This is probably the most interesting one. We have a stop transcribing function, reset, and prepare engine. So let's look into transcribe because this is the only function that actually gets called in our UI to do the transcription. So if you remember from our UI implementation here, we have a stream that we get from the speech-to-text service transcribe function. So it has to return an async throwing stream. So we can use the for try await syntax here. So this is how you create one of these, and then you have a continuation and you can yield values into the continuation to have a new entry in the stream. This is very similar to how combine was used back in the day. In there we create a task because this is an async throwing stream. We have some safety checks that our speech recognizer is already created and that it is available on the device. And then this is basically the interesting part. And as you can see, it's actually not that much code. There's just quite a bit of overhead and some error handling in here. The interesting thing is to do the speech transcription, we need a speech engine and a speech transcription request. And we create these in the prepare engine function just to keep this code a bit more organized. So let's have a look at the prepare engine function. You can already see this returns an AV audio engine and then SF speech audio buffer recognition request. So quite a mouthful. And then this is basically just a bunch of setup code for an audio session, making sure to set the category to record with a measurement mode and duck others options to make sure that the audio is clean and usable for our use case here. Then we create our audio engine. We do a bit more setup here, but that's not too interesting, I believe. Second thing that we return aside from our engine is our recognition request or speech recognition request. So we create that over here. It's important that we set should report partial results to true because that's what we want to do. We want to stream in the audio. We also want to add punctuation because the user might say multiple sentences and use periods or question marks, for example. And we're also going to tell the audio recognition request that this is in fact a dictation. This just helps it internally to be a bit more accurate. If we want to, we can set requires on-device recognition to true to only use the on-device models, but in our use case, it doesn't really matter. All right, then we do some more setup. We prepare our engine, then we start it and we return our engine and our SF speech audio buffer recognition request. So once we have called prepare engine here, we are now locally storing our audio engine and our request. And then we are creating our real recognition task here. And once again, there's a lot of state checking and error handling up here, but actually it's pretty simple. So with our recognition task, we get a result and an optional error here. So if we have an error, of course, we show some error state and we reset the speech-to-text service. Not really important right now. You can, of course, change the implementation for your own app. What's interesting is that we now use the continuation that I mentioned beforehand from our async throwing stream. So we can iterate over these results and we yield the best transcription as a formatted string. This works because we said should report partial results to true. And just as a reminder, we get this transcription here within the closure of our recognition task. This result object is actually of type SFSpeechRecognition and it doesn't only have a best transcription, it also has an isFinal property. So if the transcription is final, we will finish our continuation. So the for loop will then stop. And we will also reset our speech-to-text service to be clean again for the next dictation. Then, of course, we also have a stop transcribing function and a reset function. You can look into these yourself if you're interested. Once again, this file is linked as a GitHub gist in the video description. And there we have it. We have successfully added dictation to our local AI chat app only using on-device first-party Apple framework. So this is actually super easy. SFSpeechRecognizer also works pretty accurately as far as my tests are concerned, and the community feedback that I've heard, this is a big improvement over the old APIs that we've had previously. Of course, SFSpeechRecognizer is only available in iOS 26 and up, but that's totally fine for our use case as we're using foundation models, which is also only available in iOS 26 and up.